Um, okay, so hello and good morning, everybody. I am glad to have you here and to listen to my presentation, which is for enhancement comparison between coherent enhancement, PNN, probabilistic neural networks, and convolutional neural networks in the Taranaki Basin, New Zealand. My name is Pedro Mora, and my advisor is Dr. Heather Biddle. My committee members, which I am very glad to have them here today, Dr. Kurt Marford and Dr. Brett Carpenter. So let's moving forward. So this is the outline. First, I want you to show the reasons to work in this research. Then I will move to the geological setting and dataset. Third, I will move to the introduction and fundamentals. So I will briefly talk about the methods I am using, and then I will move to explain the methodology. And finally, I will show the results and the conclusion. So motivation. Fault enhancement methods, they help the interpreter to map discontinuities in seismic volumes. So as interpreters, we map faults using fault probabilities, usually co-rendered with amplitudes, but different methods exist, and the difference between them are evident. So you can see here the variance, a variance volume for Pedro, for probability volume, and a self-organized map classification to enhance faults and structures in a seismic volume. But usually, these methods they enhance other features such as channels or noise. For example, you can see here a lot of noise. However, they usually enhance just additional noise and channels. And here in the lower right, you can see fault objects, which are interpretations. And these peaks are the basis for a fault object. So essentially, attributes they help the interpreters, but they do not provide fault objects by themselves. So there are several attributes and methods to detect faults, but I want to point out three general approaches in those methods. So the first one you can see here is a window-based analysis. Here the methods identify the position of one sample and then analyze the surroundings using a specific window size. A second type of analysis is an individual sample analysis. We can analyze just one sample and explore all the characteristics of that sample. But we can analyze responses such as different seismic attributes and then identify if that location is a fault or not. And a third approach, I'm calling here pattern search analysis, creates a moving window that scans an image to find the patterns or to find objects. In our case, the faults or the method that I am using here is convolutional neural networks. So this research analyzes an input volume and calculate three different fault probability volumes using multispectral coherence, probabilistic neural networks, and convolutional neural networks. To create a better result, what I am using here is a fault enhancement process to extract at the end of the workflow to extract fault objects and then compare all these methods. So the question here is which workflow provides better images? Which one provides good results in a reasonable time? That's what I did this comparison using extracted objects. So before we move to the fundamentals and the introduction, I will present the area of analysis and the dataset that I am using. Now here you can see the map of the Taranaki Basin showing major structural areas such as the Western Stable Platform and the Eastern Mobile Belt, some sediment thicknesses. This area has a geological history divided mostly in four episodes, which are these episodes here. First is the Gondwana breakup, then a passive margin configuration, then a third stage of basin shortening. But now the basin is under sectional configuration, and that's about 5 million years ago. So the section in the lower left, you can see this cross section here, just this red line in the map. Um, and it shows the sediments, which are mainly Oligocene and Miocene, and the structural features that you can see here is the Cape Egmont fault zone. And this is the area that I am working on. This is small volume here. And the dataset. Here you can see the area of analysis in red. This is the area. This is a cropped area from the Maui from the MAGWE dataset. The dataset is a 3D merged pre-stacked time graded volume with a 25 to 12.5 meter bean size and a sample time of 2 milliseconds. The time section that I am using it's 200 is from 200 milliseconds to 2500 milliseconds with an SCG reverse polarity convention. And here are some faults that I am analyzing here. Then I will move to the introduction of fundamentals. So I mentioned coherent enhancement previously. We know that different attributes can be calculated from a seismic volume. Some of those attributes they can be instantaneous attributes or maybe ABO attributes, more complex attributes. Well, in the first method that I chose, I am using coherence. Coherence is a geometric attribute and is a measure of the seismic waveform similarity based on a sample comparison with its surroundings. That's why I'm calling this like a window-based analysis. In this study, I am using multispectral coherence. But what is this? Multispectral coherence is a combination of several discontinuities from different spectral components, similarity volumes. Let's say it's a single attribute with all the spectral bands discontinuities. So it's a combination of all discontinuities from several spectral volumes. This attribute shows better discontinuities than the typical standard coherence. So that's why I'm using that attribute in this workflow, in the first workflow. In this slide, you can see an amplitude section from the Great Salt Basin. This is the location map, as you can see here, in New Zealand, in the southern Iceland. Um, and here you can see coherence calculation and then the co-rendered coherence with the seismic amplitude. As you can see here, you can see that the coherence is enhancing some faults, but is also enhancing other features such as channels, noise, pockmarks, and mass transfer complexes. Now let's move to the next method. Then there's PNN or probabilistic neural networks. Probabilistic neural networks, they are widely employed in classification and pattern recognition. Lubo et al. Research, they present a salt or no salt classification, and they also present a probability volume. In this case, this is what we want to find, a probability volume, but a fault probability volume. The PNN has 4 layers and employs a probability density function and a non-parametric function to approximate the initial class. So this is a feed-forward convolutional network. So basically, the analysis is just going in just one direction. But that's another that's a more complex topic. In the PNN, in this analysis, we use several attributes as an input, and then we select samples to create the training from different attributes. So let's say I am selecting 9 attributes, and then each sample it's gonna be selected and extract some training, and then it's used as an input for the exhaustive PNN workflow to find the best attribute combination and create the full probability volume. This is the result of my test in the Great Salt Basin in New Zealand. And again, you can see faults, but you can see also other features that are non related to faults. This is the co-rendered result. So in this example, in the Great Salt Basin, I use aberrancy magnitude, GLC entropy, GLCM homogeneity, Sobel filter similarity, and envelope, just to create this full probability volume. And convolutional neural networks. This is the third method that I'm using. CNNs usually have several convolutional layers, or let's say filters. By applying these convolutions, here, uh, these convolutions can create contrast or maybe directional filters to differentiate the characteristics from an image and identify patterns or objects. So a moving window can scan the image and try looking for specific patterns and can predict objects. But before predicting, the CNN needs training. So the training must be completed with several training datasets from the same object to identify critical patterns. In this case, the CNN fault prediction algorithm is using it was trained with synthetic models. So that could be an important factor for the results that I am having. And here you can see the result of the CNN fault classification co-rendered with an amplitude section. And this is the fault enhancement process. It's an additional method to sharpen and smooth the previous results from fault detection processes. So basically, in the input attributes, we can use the PNN or CNN or coherence, multispectral coherence. And then we can create a fault probability volume. And then, as an additional step, we can skeletonize the result. This method is based on Key et al. 2018. Basically, they created an eigenvector process to identify fault probability and fault directions from using a fault probability volume. This is the result. So here you can see the deep magnitude. Oh my god. The deep azimuth, and this is the final result, which is fault probability. Now let's move to the research, to the workflow and to the methodology. This methodology shows different colors to mark different workflow stages. So first, I employ a data conditioning process. You can see here the data conditioning process to remove undesired features. So what I did was to use footprint removal, spectral balancing, and structural oriented filtering. The second step is to run the different fault enhancement methods, such as multispectral coherence, PNN, probabilistic neural networks, and CNN. So at this point, I have three different volumes. Now, what I did was to apply the fault enhancement process from Key et al. 2018 to create a final skeletonized volume. So in this step, what I did was to extract all the objects. How do I do that? So basically, I use a partially interpreted fault um, as the guide for the extraction process. So I extracted the same fault 3 times. In this case, I am going to explain that in the next slide about the active control method. But basically, I am creating what I did was to use an algorithm to extract faults using partially interpreted faults. And finally, the final step here is compare the results from three different methods. I have a different fault set, which I am calling the fully interpreted fault set. And this is the ground truth of the analysis. So I am comparing the fully interpreted fault set to the extracted objects from the different volumes and workflows. Now let's move to the okay. So the results. Now I'm showing you the results. This slide shows two different interpretations of the seismic volume. The full interpreted fault set is the ground truth to compare the extracted objects. This second set is the partially interpreted fault set, and is one of the extracted. Is the one that I use to extract objects from the different fault volumes. And this set that you can see here is the surface, but basically they are used to extract the training for the PNN workflow. And the results again. So here, these are the results from the coherent enhancement for the coherent enhancement process. You can see the difference between non-conditioning data and preconditioning data. The section shows a clear difference between them. The upper section, you can see a salt and pepper texture that dominates the entire section, and plenty of noise. And in this lower section, you can see that there is a better continuity here in the faults, here. And actually, you can see that also here in the time slide, in this time section. So red, green, and black arrows, the arrows you can see here, you can show differences between the data set, and the time slice also shows better results. This is for the coherent enhancement. The PNN result. So the figure on top, you can see the methodology based on Google et al. Work to obtain the classified volume. So attribute calculation creates the input for the PNN. Then what I did was extract samples for each attribute, and then test all the combinations. to see which is the better or the optimal combination for the PNN. To define the attribute combination, I created the model for the PNN, and then I classified the volume. So there are more steps in the methodology that you cannot see in the workflow that I showed in the previous slide. So here I selected 9 attributes as an input, and the final classification employs just 3 of them to create the result in here in the lower part of in this lower part of the slide. So variance in magnitude, multispectral coherence, and solid filter similarity. But again, you can see plenty of noise, a lot of noise in both sections. Although in the lower part you can see less noise, there is still a lot of them, a lot of that in both sections. And the CNN, here are the CNN results. So the difference between non-conditional data and conditional data is most related to the number of artifacts. So here you can see, for example, here you can see a continuous fault, but in this case you don't see that continuity in the non-conditional data. So at this point, I don't know if you can notice that, but there is in the middle section in this part, it has more noise, but that's because of the sedimentological pattern in the section. Now, object extraction. This is the method that I'm using to extract objects. So an active contour, that's the method that I am using, is a deformable line influenced by image forces that pull the line towards the feature or the fold in this case. This is the methodology that I use. Basically, I picked a few fold sticks, then I interpolate between those fold sticks, and then I apply the algorithm in each section. So the algorithm result is that what the algorithm does is just this is the initial line, the red line, and then the final result is the blue line. So basically, the red line is trying to fit the shape of the fold in that section. This slide shows a detailed view in a cross section of the three classification results. The detail area here in the section shows plenty of chaotic reflectors, and the fault is mapped in this detailed section. So the coherent enhancement classification shows noise and salt and pepper texture in this area. You can see here that. But if we move to the PNN, shows heavy noise and artifacts and unrealistic faulting compared to the coherent enhancement. And then we move to the CNN. As you can see, the result is cleaner and sharper, but numerous artifacts can be found in the result. So, for example, this really weird fault. The CNN shows promising results, but strong artifacts. So, coherent enhancement and the coherence enhancement shows noise, and the PNN overall it shows poor results. So the active contour result, you can see that the results too. So basically, it can the line in here can tries to fit the feature, as you can see here in the CNN4 result. So here the line is following the high probability values, and then it jumps to the next or close for high probability. So basically, the algorithm is trying to fit the shape of the fault. This is the house of distance. It's a common method to measure distance between the 3D surfaces. Since we are comparing these methods, I am using an additional tool to see the difference between the methods and the ground truth, which is the manually mapped fault. I measured the distance between the extracted surfaces and the manual interpretation as an additional way to see the differences. 3 faults inside the 3D volume are presented here. Blue are low values, and red are the maximum measured distances in the meshes. Basically, it's the highest value is 100 meters. The coherent enhancement mean distance, you can see here in the table, is 17.8 meters, and the CNN mean distance is 18.3. So the CNN has a higher mean distance between the ground truth and the surface. So although it's a very small differences, a very small difference, I consider that that artifacts are influencing this result in the CNN mean distance. Also, you can see that there are anomalous areas consistent in the three different in the three different in the methods. I mean, you can see these red values here, red values here. But I think that this behavior is related to the manual interpretation, since the interpreter um, like dictates the default position, the real position is not mapped properly in these points. So I think that that's the problem with these red colors here. Now this is the section of near the Maui tree well. There are four sections, or let's say four differences in results to the fall enhancement, and these are related to sedimentation patterns and structural framework. The section 1 shows clear reflectors and strong amplitudes. The section 2, this section here, shows clear reflectors and strong amplitude values. Chaotic and mostly discontinuous reflections, low and medium amplitudes. The section 3 is mostly parallel continuous with moderate to high amplitude reflectors. Now, the section 4, it's more complex uh, because it shows high and low amplitude values, but you can see also several cut reflectors due to the heavy faulting near the Cape Egmont fault zone. This is the Cape Egmont fault zone. Also, in this part of the area of analysis, I have acquisition footprint and a lot of noise, which heavily contaminates the eastern part of the dataset. Mm, and this is the comparison table that I am trying like to summarize all the results. So in terms of interpretation use, the coherence method enhances fault at a reasonable scale, um, from detail to large scale. Since the analysis window is can be very small, so it can enhance plenty of details based on coherence. In the case of the CNN, I think the method shows better results in large scale scenarios and should be used in large and local scale analysis. The PNN shows poor results. You saw that in the previous slide. So I think the capabilities of the PNN are not proven at all, at least in this area of analysis. So the workflow complexity and the time invested just to create the full probability volume. The PNN needs 40 hours to and uses 10 attributes. That's a lot of time. Um, well, this is for a 3.5 gigabyte volume using 60 processors. In contrast, the CNN and the coherent enhancement method, they use two attributes, three attributes, but the time is around 2 hours to 3.5 hours, depending on the parameters you set for these algorithms. So, yeah, in this case, the PNN actually you need a lot of time just to run this process. And the coherence, the mean distance, we talked about this in the previous slide. So it's slightly lower in the coherent enhancement and the CNN in the comparison between coherence and CNN. So I think the coherent enhancement gets or finds closer values to the real position of the fault. The PNN has a lower mean distance, but because it has a lot of noise, I don't trust these results since the algorithm might be following noisy probability values around the faults. So, and I think it's not reaching the real position of the fault. Now, the conclusions: the data conditioning improves the fault enhancement and removes plenty of noise and some artifacts in all workflows. The multispectral coherent enhancement could be a better choice for CNN than CNN for small faults analysis because the small due to the or because it has a window analysis approach and a small size of the window. The CNN enhances large faults and small discontinuities. They are ignored. In that sense, CNN shows a clean volume, but it generates some artifacts, and interpreters must be aware of these problems. A new training or maybe post-processing might correct these issues. So, PNN sampling and attribute selection heavily influence the results. Well, this is a conclusion for the PNN workflow. Sampling and attribute selection heavily influence the results if the interpreter is not selecting the correct set of attributes, or maybe selects an incorrect training, then the results will be poor. The PNN also shows a strong noise in the Taranaki basin, but more research must be done in subtle fault analysis and small data sets. The test set that I use in the Great Salt Basin, uh, well, it shows some noise, but not so heavy as the results in the Taranaki Basin. Maybe this is related to the size of the analysis, because this is a 3.5 gigabyte volume from 200 milliseconds to 2500 milliseconds. I think the PNN employs different attributes, so maybe it could be a richer. I mean, it has the potential to use or to give us more information. And final conclusion on active counters, they might follow anomalies such as stair step or artifacts, so the results must be analyzed to avoid errors or misinterpretation. The user input also can add some uncertainty to the object extraction. So because the method is just following like the guide of the interpreter, so this also can create more noise, create noise or errors. So I like to acknowledge to the New Zealand Petroleum and Minerals, because they provide the dataset, to Schlumberger because they provide the license for the software, to the ASPI consortium because they support our work, and to the SDA agency at the University of Oklahoma for their support and suggestions, and especially to David Luo and Tang Ha for their comments. Uh, those comments were awesome. Uh, and I will also like to extend my deepest gratitude to the to the Saldarriaga Concha Foundation and the Fulbright program, because this research and my presence here actually would not have been possible without their support. And I would like to extend my appreciation to the committee members. First, I would like to express my gratitude to my advisor for her guidance and conditional support during my time here. Thank you very much, Dr. Pedro. And I also want to express my appreciation to Dr. Marford for his invaluable contributions, suggestions, and guidance in this project, and to Dr. Carpenter for his constructive advice during this semester. Many thanks to the OU faculty and staff for their help and kindness, and to the SCG chapter and geoscience students for their company and good moments, to the Colombian Student Association and Joanna Walshap for their support and friendship, and to all the folks and friends who share their time and affection with my family and me, and finally to my family, and especially to my mother who joined me in this journey. And thank you to you all, and it will be my pleasure to answer